Actually, it's sort of my dream to do a series where I teach huge YouTubers math. Um, so if anyone out there has connections with enormous YouTubers, I think that we could really make math popular, which is going to make the world a better place. Okay, guys, I got a really great video for you today. So today I'm going to be teaching my niece a little bit of number theory. So a little bit about Grace Pavlov. She is a second-year university student at Queen's University in Belfast studying politics and philosophy. And I don't think she's taken many math classes, so this should be quite interesting. Another thing that's super important is that she is one of the co-hosts of my non-math podcast. So it's called the Penn and the Pavlovs. So it's me, Michael Penn, and then Grace Pavlov and Alexei Pavlov. They are brother and sister. And the podcast is, I think it's really funny. I think you guys should check it out. I think we've got really great banter and so forth. So anyway, make sure to go and check out the podcast. There is a link in the description. And now I'm going to teach her some math. It's going to be great. Okay, so Grace, how are you feeling about this whole little experiment that we're doing?
This is so exciting.
Okay, well said, I think.
Yeah,
okay.
I don't have the best. I don't know. I don't like this whole number theory thing. I don't know if I'm gonna like it.
I think we're gonna be great. I think we're gonna be great. Okay.
Like, have you ever done music theory?
Yeah, I don't think it's the same at all.
Well, I know it's not the same, but I did not like music theory, so I don't think I'm gonna like this.
So you don't like things that end in the word theory?
Yeah, maybe.
Is that sort of the link that you're trying to make here?
Yeah, maybe. And it may be just a bit ironic given that I study theories.
Sure.
Of a different kind.
Okay. So there's this like kind of classic style of number puzzle that happens in like this so-called recreational mathematics, which is this find the last digit or find the last two digits or sometimes even find the last three digits of a number which is very, very large, and it's expressed like via the exponent of one big number and another big number. So anyway, that's the type of problem that we're going to look at today. So what is the last digit of 4,723 to the power 8,675? So doing this just by straight calculation would be like essentially impossible without a computer. So I did it in a computer. And as you can see, this is the number. This is about 10% of the total expansion of the number. So I didn't count the number of digits there. I mean, you can do a quick estimate on the number of digits. I think it would be like probably 50,000 total digits or something, but that's the first 10%. So this is a really, really big number. But the tricks that I'm going to teach you will allow you to do this sort of calculation in probably less than 2 minutes. And when we're done, you won't know any of the digits except the last one. You only will know the last digit. So really, we'll just find the last digit. That's the trick here, is we won't find any of the rest of the number. And you might say, well, why would we do this? Well, I think math is like beautiful enough to do on its own, but the techniques that we're using here are part of the number theory developed by Leonard Euler in the 1700s. And they went without application for many, many years, actually until the 1970s, when it was discovered that they could be used to form a crypto system, a coding system, which is now used for internet security. So this is like the ultimate example of what in mathematics is called the golden goose, the pure mathematics that comes to application much, 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 much later. Okay, so let's get into it. So we're going to recall a couple of definitions first. And, we're not going to need these definitions except to like define this sort of thing right underneath, but just so that we make a tidy whole thing here, we're going to recall that the natural numbers is just the set of all positive whole numbers. So like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, so on and so forth. That's what we call the natural numbers. So notice that that doesn't include like a half, that doesn't include like 2 1/4, that doesn't include -7, that doesn't include anything like that, just the positive whole numbers. It sometimes includes 0. In fact, I think in Europe it includes 0. So if you were to take maths class in Ireland, Northern Ireland, where you are, it would include 0, but that's kind of neither here nor there. The comments are very excited about pointing out that includes 0 sometimes. Okay, and so then we're going to need this thing called the integers. And so that is this like fancy Z. So that's our symbol for the integers. And that's just all of the positive and negative whole numbers, including 0. So like I just realized I made a mistake here. There should be the number 0 there as well. So we've got -5, -4, -3, -2, -1, 0, 1, 2, 3, 4, 5. And then that extends in both directions. So this is all positive and negative whole numbers. So you might say, well, why the number Z, right, for integers? Well, it comes from the German word for number, which is Zahlen. Who knew? I guess I knew. Okay, now next we're going to need our like definition, which is going to make this whole thing work. And this is essentially the only definition we need to make this entire trick work. And that is, given a natural number, so that's a positive whole number, we're going to say 2 integers, so those integers are a and b. We're going to say that they are congruent modulo n. So that's the phrase that we're defining, congruent modulo n, if a minus b is a multiple of n. And then we've got this nice shorthand for that right here, which is, well, I mean, it's shorthand for the sentence right above. So you just read that as a, so a congruent to b mod n. So that's how you read that. So in order to really understand what a math definition is, you like kind of need to look at examples, right? So here I've got some examples. So 17 is congruent to 5 mod 6. So that's our first example. And so why is that? Well, let's put that in terms of our definition. So notice our definition says to do a minus b. So we do a minus b. So let's look at a minus b. So 17 minus 5 is 12. I think we could all agree with that, right? And you can say things. Yeah, you can say it's allowed.
Yeah.
Okay. So 17 minus 5 is 12, but 12 is a multiple of 6. In fact, it's 2 times 6, right? Yeah. So that's why 17 is congruent to 5 mod 6. Now let's look at this. 8 is congruent to 3 mod 5. And that's because 8 minus 3 is 5, well, times 1, but I didn't write the times 1 in there because we don't really need it. 5 times 1. So it's a multiple of 5. So the next one is 37 is congruent to 1 mod 9. And so that's because 37 minus 1, you take their difference, and that is 36, which is a multiple of 9. It's 4 times 9. So another thing to notice here is that this number over here on the right-hand side, which is maybe what we would call the reduction, can always be between 0 and n minus 1. And so that's happening here everywhere, right? So 5 is between 0 and 6 minus 1. 6 minus 1 is 5. 3 is between 0 and 5 minus 1. 5 minus 1 is 4. And 1 is between 0 and 9 minus 1, which is 8. And so somehow there's like a special number, which is maybe our best choice when we're doing this reduction. And it's between 0 and 1 minus this thing right here. Now, I mean, there's this whole thing in mathematics where you have a definition, which is what we have right here. So we have this is like the sort of careful, proper way of defining this concept. But then there's like an equivalent statement. And often the equivalent statement is better for checking examples really, really quickly. So, I mean, you'll often use the definition when you're writing proofs and stuff like that. But for doing calculations, which is what we'll do today, you don't really want to use the definition so much. You want an equivalent statement that's better for making calculations. So that's what we have on this next page. And I've just called it trick. So trick is that A is congruent to B mod N if and only if A and B have the same remainder when dividing by N. And so this is just putting everything into like 4th grade arithmetic, right? Because when you divide, you can have a remainder sometimes, right? Division with remainder, like my kid does or whatever. Now we can like very, very quickly look at some examples, and we don't have to think about the A minus B and stuff like that. And so notice that 12 is congruent to 2 mod 5. That's because when you divide 5 or 12 by 5, so 12 divided by 5, that has a quotient of 2 and a remainder of 2, right? So just like if you were to do it out in long division, maybe we could do it out in long division right here. 5 divided by 12. And so you would do, oh, I need to multiply by 2. I get 10, and then I get a remainder of 2, right? Are we cool?
Yeah, it's ringing a bell.
So there we've got a remainder of 2. So all you do is keep the remainder. So you divide and keep the remainder. That's the whole thing. And then 39 is congruent to 4 mod 7. And that's because 39 divided by 7 is 5 remainder 4. Well, let's look at that. If we do 7 divided into 39, okay, so we multiply by 5, that gives us 35. And then we get a remainder of 4. So there is our remainder. And so our remainder is what we put right here. And then maybe one more. So 80 is congruent to 3 mod 11. And that is because 80 divided by 11 is 7 with a remainder of 3. But all we care about is the remainder. And so when we're working mod whatever, all we care about is the remainder. That's really nice. And so let's just do this. 11 dividing into the number 80. So we put a 7 here. So that's 77. 80 minus 77 is 3. So there is our remainder, which showed up right here. Okay, so let's do an example together. And then I'm going to like have you work through some. It's going to be awesome.
Awesome.
Okay, so let's say this space over here will be our little calculation space like we've been using or whatever. So let's do this one right here. So we're going to do this. 18 is congruent to something mod 7. So I'll do this one. So we're going to do 7 divides into 18. So tell me what the quotient is.
2.
2. And that gives me a 14.
14.
And so my remainder is 4, right?
Yeah.
And so 4 is the only thing I want to keep.
Yeah.
That's all I care about. So that means I put a 4 here.
Yeah.
So that means 18 is congruent to 4 mod 7. And that's my reduction. Okay, so do one of these others.
Okay. Okay, so you got 125 divided by 4. What's like a big number?
Yeah, you could probably write it down or something.
Can't you do it? Oh, I haven't done long division in such a long time. Can't you divide 4 into 12 or get?
Yeah.
You can do that first, right?
Yep. That's how you do it.
Okay. I was gonna say I can't jump straight to the. Okay.
Well, I thought you would go across because the one across is easier. See this one right here?
Oh, I didn't even see that. Oh. Okay, I'll do that one. I'll do that one. All right, so that goes in a remainder of 1.
Yeah, good. So this answer is 1. So 9 is congruent to 1 mod 8.
I didn't even see that.
Or actually, hold up a minute. So tell me, in Ireland, how do people write 1s? Are they the super Euro ones like this? Maybe you don't know because you're not taking maths.
I'm not taking maths. No, I'm not taking maths.
Okay. Anyway.
Let's
carry on.
Carrying on. So I'm doing that 4 and 125 one.
Yeah, 4 and 125.
Is it also a remainder of 1?
It is a remainder of 1. That's right. So 4, 125. And so what do? We put a 3 here, which gives us a 12. That gives us a 0. You bring the 5 down. Multiply by 1, 4, remainder 1. Yeah. So the quotient is 31, which we don't care about actually.
Yeah.
And the remainder is 1.
Cool.
So a really quick way to notice this is that 120 is divisible by 4.
I was going to say.
Yeah. So since 120 is divisible by 4, you can actually just totally forget about this this first bit right here. The 120 out front just doesn't even matter. You can immediately reduce that to 5, and then the 5 can be reduced to 1. And if we were to do this like more, we would do those kind of tricks very, very quickly. Okay, what about the next one?
We'll do the 67 and 9 one. Now I learned a trick in school. Okay. So I don't know.
Learned a lot of tricks in school.
Yeah. So when you divide by 9, right, you can do so 9 goes into 67 7 times.
Yeah.
Well, goes into 63 7 times.
Yeah. And then your remainder is
4.
So that's right.
Yeah.
Yep.
Do you have like the finger thing? So if it's like,
yeah, maybe, I don't know.
Okay, well, do you want me to explain it?
Sure, go.
Okay. Because that's how I did that. Or got the 9 to 60 into 67. So it's like, well, I guess this is backwards. So like 9 times 4, 1, 2, 3, 4.
Yeah.
16.
36.
Oh, 36. Well, yeah. 9 times 5, 45.
Oh, cool.
9 times 6, 54. 9 times 7, 63.
63. Oh, that's good. Yeah. There's this other trick that if you take the sum of the digits of a number, you get the same remainder when dividing by 9 as the original number.
Yeah, that sounds like a lot more.
So that seems like a lot, but it's actually a lot easier. What's 6 plus 7?
13.
13. Now what's 1 plus 3?
4.
4. That's your number. You just keep doing that until you get a number between 0 and 8. Yeah. So that's a cool trick also, right?
Wow, very cool.
Yeah. You could prove that using this kind of stuff pretty easily, but we won't do that. Okay, now the last 2 examples are really important for our problem, as we'll see later, and that is working modulo 10. Because remember, our goal is to find the last digit of this like crazy number, right?
Yeah. Makes sense.
That crazy number is probably like bigger than the number of particles in the universe, by the way.
Really?
Probably. I don't know.
I thought you were giving me a fun fact.
Well, I mean, we can give it a googs if you want. I mean,
nah, it's okay.
Yeah.
So is it remainder 7?
7.
Cool.
Yeah.
I'm not doing too shabby.
No. I'm very good at teaching math.
Okay. We'll look at it like that as well. I just thought I was smart. No.
It's a confluence of these 2 facts.
Okay, fair enough. Okay. Just give me a second.
Yeah, just don't try too hard. Think smarter, not harder.
So it goes into 10 goes into 37 3 times.
You're thinking harder, not smarter.
What? Oh, are you going to tell me to add them up and then?
No, that only works for 9.
Oh.
Anyway, keep going.
What do you mean work harder, not smarter?
Look, 7, 7.
7?
No, look, this thing ended in a 7.
Oh, 2.
2. Yep. So it's 2 because 3, 7, 9, 6, 2 is equal to 3, 7, 9, 6, 0 plus 2. Yeah. And this guy right here is a multiple of 10.
Can't see it. Oh, there it is.
Yeah, that guy right there is a multiple of 10. So whenever you're working mod 10, it's like really easy. All you have to do is look at the last digit. Whenever you're working mod 10.
Oh my gosh. So we can answer the question.
I mean, we can almost answer the question.
So is it not 3?
No, it's 3 to the 8, 6, 7, 5.
But then that's the shortcut.
Yeah, so that's the first shortcut.
Oh,
okay. We got to pause a second. My headphones just went weird, and now I have it through the thing. So just hold tight. I'll BRB. Okay. Wait.
Okay. I'm gonna eat some of mine.
Yeah.
Well, while Michael figures that out, I like to share with you guys my favorite chocolate, the Aero Peppermint. Now, this is a pretty big chocolate bar. I don't know if you guys can tell, but that's like longer than my hand. You don't know how big my hand is, but it's smaller than this chocolate bar. And it was £1, which is probably like $1.20. But I feel like regular chocolate bars back home are like a quarter of this size, and they're $1.20 anyway. So this is my favorite chocolate. I don't really think you can get them back home in the States. But you international folk, what's your favorite international candy? Or, well, not, I guess it's just candy, because it's only international to me. It's national to you, right? If that makes sense. I don't know. I'm just trying to not sit here awkwardly while Michael gets his headphones prepared. Oh, and he's back.
So now I hope you guys enjoyed Chocolate Talk. That's a new segment.
I thought, given free range, I took the opportunity by storm.
That's good. Okay, so you have almost solved the problem, right? So you just determined back here that we really only need to look at 3. Oh no, that's supposed to be my highlighter. 3 to the 8, 6, 7, 5, right?
Mm-hmm.
Okay, but that's not super easy to do in itself, right? Yeah, but there's a trick. I mean, there's a trick. Otherwise, there'd be no point. And the trick is this. And so there's for anyone out there who wants to know, although a bunch of my viewers already know this, is that what's going on in the background here is something called Fermat's little theorem. And its generalization, which is called Euler's theorem, or sometimes Euler's generalization of Fermat's little theorem. We're not going to state that super carefully. We're just going to look at some results of that. So the basic fact here is that exponentiating numbers modulo n creates a pattern. And you can use that pattern to simplify these things really quickly. Okay, so let's fill in this chart. And by filling in this chart, we'll see a pattern. Do we need vertical lines there for the chart?
Oh, you're doing it anyway.
Yeah. Okay. So 3 to the 0. Okay. So pop quiz from high school algebra. I don't know. What's 3 to the 0?
0.
Oh my goodness.
No, is it 1?
Yeah, it's 1.
Those two are very confusing.
Yeah. Okay. So look at what we're trying to do here. We're trying to look.
Wait, why is it 1?
Why is it 1?
Yeah.
Okay. So it's like this. Okay. So let's step back a little bit. So 0, the number 0, right, is the additive identity. And what I mean by the additive identity is if you add it to any number, it doesn't change that number, right?
Mm-hmm.
So 5 plus 0 is 0. Is that Alexi?
No.
Okay. So 5 plus 0 is 5, right?
Yeah.
Okay. Yeah. It didn't change the number. Well, it turns out if you add nothing together, you get the number 0. So if you just add nothing together, you get the number 0. But then 1 is the multiplicative identity. So 1 times 9 is 9, right? So 1 is the
I remember that.
Yeah, 1 is the special number so that if you multiply it by anything, it doesn't change it. And so if you multiply nothing together, you get the number 1. That's just what we take to be true. So if you add nothing together, you get 0 because it's the additive identity. If you multiply nothing together, you get 1 because it's the multiplicative identity.
Cool. All right.
Yeah, so there's probably a different way to explain that that's better, but I failed. Okay. So now what we're trying to do is look for a pattern of 3 to the power k mod 5. So that's what we've got here. 3 to the k mod 5. So that means we're going to exponentiate and then reduce mod 5. Okay, so what's 3 to the 1? Don't think too hard.
3.
Good. And now let's do each of these. So 3 squared. So tell me, what's 3 squared?
9.
9. But we don't want to work with 9 because we're thinking about mod 5. So we only need things between 0 and 4. So if we reduce 9 mod 5, what do we get?
If we reduce 9, 4.
Yeah, 4.
Yeah.
Yeah. Perfect. And now
Wait.
3.
Okay.
Yeah, because 9 divided by 5 gives you a remainder of 4.
Why didn't you do the mod 5 for the 3?
Because 3 is small enough so that you don't have to do that. So think about this. If you do 5 divided into 3, right? You get a quotient of 0. So that's 0. And you get a remainder of 3. See? So if the number is small enough, you don't have to do that reduction. Okay, so we've got 4. Okay, that's good. And now we're going to calculate 3 cubed. Okay, so there's a couple ways to do this. You could do 3 times 3 times 3, which is 9 times 3, which is 27, right? But yeah, like that. But let's work smarter, not harder.
No, that was pretty snippy.
Yeah. But we can do it even easier. So we're working mod 5. So let's write this as 3 times 3 squared, right?
Yeah.
Now that's 3 times 4. You might say, well, why is it 3 times 4? That's because up here we saw that 3 squared was equal to 4. So look at it. We've got something easier to do, right? So what's 3 times 4?
12.
12. Oh, no, that's not the right color.
Oh, my gosh. I thought you were going to say, oh, no, that's not the right answer.
No, that's...
I was like, wait a second. Jeez. Okay. Yeah, I got it.
But now if we reduce 12 mod 5, what do we get?
7. That's wrong.
Keep going. No, that's right. 12 and 7 are congruent mod 5. But if we want to go all the way down.
What do you mean all the way down?
Remember, we should go all the way to a number between 0 and 4.
So mod 5 again?
Yeah.
2?
2. Yeah.
Huh.
So look, let's do it over here. So 5 dividing into 12. So you get a quotient of 2. That's 10. Subtract those, you get a remainder of 2, right? So, but I mean, you figured it out. You can repeatedly subtract 5, or you can do this division problem over here. They yield equivalent things.
Oh.
See?
Yeah.
Okay. So now let's do 3 to the 4 power. So again, let's work smarter, not harder. So how can we do that working smarter, not harder?
4 times 4.
Yeah, or 3 times 3 cubed.
Well, yeah, and then I skipped the...
Yeah, we can just use...
and then 3 times 2.
3 times 2, which is 6, which is equal to...
1.
Okay. So now...
Just like patterns, man.
Now let's see what we've got going on here.
Oh, exponential numbers creates patterns. Oh.
Yeah. That's what I already said that. I started.
I know, but I didn't register that until now.
Yeah. So look, we made a so we've started making a loop, right? So
yeah, because we're back down at 1.
1 goes to 3, goes to 4, goes to 2, goes to 1. What do you think the next one is?
2.
No.
Is it 3?
So, yeah, we're multiplying by 3. So at each step, we multiply by 3, right?
Oh, okay. Yeah.
So multiply by 3, you get 3. So multiply here by 3. 1 times 3 is 3. Okay. 3 times 3 is 9, but 9 is the same thing as 4. We discussed that. 4 times 3 is 12, but 12 is the same thing as 2. We discussed that. 2 times 3 is 6, but 6 is the same thing as 1. Right?
Yeah.
Because we're working mod 5.
Yeah.
Okay. So that means that we put a 3 here. 3 times 1 is 1.
Then it's going to be 4 for the next one.
Yeah. And then 2. And then 1. And then
3,
and then
4,
and then, well, now it's just going to continue forever and ever 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 and ever. But now check it out. Now I think you could probably see where our trick is going to come in the future. But now we can easily reduce 3 to the 891 mod 5. And how can we do that? Well, we want to notice the length of this. It's a cycle. So I like to think about it with a picture. And, I say I like to think about it like it's so unique to think about it like a picture, but it's not. Like everyone thinks about it like a picture. So you've got the number 1 up here, right? And then over here, you have the number 3. Then you have the number 4 down here and the number 2 down here. And then you have this loop like this. And these arrows mean that we're going to multiply by 3. And then maybe we'll put some context in here that we're working mod 5. So we've got that kind of loop, right? So if you do it 4 times, you get back to where you started. And so in this case, the loop has a length of 4. Oh, that's not supposed to happen. So the loop has a length of 4, right? You got to nod a little bit more aggressively.
Yes.
Yeah,
yes.
But don't hurt your neck. And that's special to this number 5, right? That's every number. Okay, close one. So every number that we work with is going to have potentially a different loop length for what it's worth. So you kind of have to build this chart to start off with so you know what your loop length is. Okay.
That was a terrible arrow.
Yeah, well, Okay, so now let's look at this down here. We've got 3 to the 891 is congruent to something mod 5. So let's do that. Well, let's first notice that this loop length tells us that 3 to the 4 times anything is equal to 1, right? And that's because, well, every time we get 4 copies of them, we get 1, right? Yeah.
And then 3 would be 2, and then 2 would be 4.
No, and then like 3 to the 4 times something plus 2, for instance, would be equal to 4. So the takeaway here,
what?
Yeah, go.
Wait, so, okay. If 3 to the 4 times something equals 1, and then 3 to the 4, so what 3 to the 4 being 1 plus 2 equals 4, wouldn't that mean it equals 3?
Yeah. But you got to remember exponent rules. This is the same thing as 3 to the 4 raised to whatever this box is times 3 squared. So they're like these exponent rules from algebra.
Nah, I'm too far removed. Okay, never mind. Never mind.
But there's a quick takeaway which we can put in terms of what we already talked about. And it goes like this. So because our loop has 4, maybe is length 4, maybe let's use that terminology, is length 4. See, there are 4 things over here, right?
Yeah.
There are, yeah. The exponent can be reduced mod 4. So tell me, what is 4 mod 4?
1.
0.
Oh, yeah.
Yeah, 4 mod 4 is 0. And notice 3 to the 4 is the same thing as 3 to the 0.
Gotcha.
What is 9 mod 4?
A 0.
No, 9 mod 4.
5.
Yeah, but further down.
2.
No.
3.
No.
1.
1. So
okay, you lost me on that one.
9 mod 4 is 1 because 9 divided by 4 is 2 with a remainder of 1. Yeah. So 9 mod 4 is 1. And now notice that 3 to the 9 is the same thing as 3 to the 1.
Yeah.
Yeah. Okay. So now, like I said, we can easily reduce 891 mod 5. And we do that by reducing this exponent mod 4. So we want to reduce this exponent mod 4. And that all comes from this like observation that we saw up here, that because our loop is length 4, the exponent can be reduced mod 4. Okay, so let's do that. We'll divide 4 into 891. Remember, that's how we reduce 891 mod 4. So tell me, what is, how do you do this? So 4 goes into 8 2 times, right?
2 times. Yeah.
That gives
4
us a
goes
remainder of 0. 4 goes into
yeah.
9
2 times.
2 times. That gives us a
Remainder
remainder of 1. I guess I'm skipping it. Bring the 1 down. 4 goes into 10 or 11
2 times.
2 times. And the remainder is
Reminder's 3.
3. So that means this thing should be the same thing as 3 to the 3 mod 5.
Okay. Yeah.
And this is because 891 is congruent to 3 mod 4. And so there's this trick where you can reduce the exponent mod something. But we made a chart up here and we determined that 3 to the 3 was 2. So this is 2 mod 5. Right? Okay. So I got two for you to try over here.
Oh boy, oh boy, oh boy.
Yeah, so let's paper it up, and then you're gonna look.
Okay. So 3 goes into 7. Hold on, let me write it out. 7. 3 goes into 7 2 times. 6. Boom, boom. That's 14. 3 goes into.
Whoa, wait. Why are you doing 3 into 7? Look at our highlighted thing up here.
So so we do 1.
What do you mean
because
we do 1?
Our loop is length is 4. The exponent can be reduced mod. Oh boy. I don't know.
So what's our exponent?
1.
No,
3. Oh yeah, that. Oh, okay. I thought you were talking about the exponent of 3 would be 1. That's okay. Okay, yeah. Exponent is 7. Oh, so then we do 742 divided by 4.
Yeah, so do that.
Oh yeah, you're right. Yes.
I'm often right.
Oh boy. So that goes into it once. Boom, boom. 34. 4 goes into 34. How many times? 5, 20, remainder 2. Okay, remainder's 2.
Remainder is 2. So tell me the final answer.
185, remainder 2.
Yeah. We don't care about that though. What's the final answer of this whole thing?
Oh, 3.
No. So here, let's talk it through. So because 742 is congruent to 2 modulo 4, 3 to the 742 is congruent to 3 to the 2 mod 5 because of this rule right here. Right? Because of this rule right here. The exponents can be reduced mod 4. But now what's 3 squared?
9.
Which is?
4.
4. So the final answer is 4. All right, do another one. Do the next one.
I need more paper. I've run out of space. Wow. Okay. Well, what was that? Okay, so we're gonna do the 4 thing, right? So 1,237 divided by 4.
That's right.
Yeah. Okay. Just making sure. That goes into it 3 times. 0. 4 doesn't go into 3.
Yeah, so 0 times. So you have to move to the next.
4 times 0 is 0.
Yeah.
Okay, wait, now I'm confused now. Oh, I was doing so well. Now I'm struggling with long division.
Yeah,
Okay.
well, it gets the best of us.
Yeah. Okay. So you have 4 goes into 12 3 times.
Yep.
4 times 3 is 12. 0. Bring the
Mhm.
3 down. 4 doesn't go into 3. So that's
0 times.
so yeah. So now up top you have 3 0.
Now you bring the 7 down. So four
Oh.
goes into 37.
Oh. Oh. Shortcut. 4 goes into 9.
Yeah.
Not
Remainder.
yeah. 9 times 4 is 36.
Yeah.
Remainder 1.
Remainder 1. So what's their final answer?
Not remainder 1.
No, it is.
It
So
is?
it's
And
3 to the 1.
Oh.
So 3 to the 1,
3.
which is 3. Yeah.
Oh, boy,
So let's write it down. So because
oh, and then because the remainder was
1237 is congruent to 1 mod 4. 3 to the 1, 2, 3, 7 is congruent to 3 to the 1 mod 5. But 3 to the 1, that one's really easy. That's just 3, right?
Yeah, it's super easy.
Okay. So let's do this practice. So let's do this one. Okay. So we'll do this together.
Yeah.
So let's see. We want to find 7 to the 4, 3, 1 mod 9. So in order to do that, we need to first make a chart that makes our loop for 7, right? Because a priori, we don't know how long our loop should be. We know that a pattern should be created by this fact over here, but we don't know what that pattern should be yet. So let's find that pattern. So let's find K, so some numbers K, and then some numbers 7 to the K mod 9. Okay, so we'll do 0, 1, 2, 3, 4, 5, 6, 7, 8. Okay. So let's do these a little bit at a time. So what's 7 to the 0 power?
1.
1. What's 7 to the first power?
7.
7. So good. We're off to a good start. What's 7 squared?
49.
49. Okay, but what's 49 mod 9?
5. Oh, no, because it can't go into that, can it? 49 mod 9.
Yeah, so what's a multiple of 9 that's pretty close to 49, but smaller?
Then 5. Smaller than 5, right?
No, smaller than 49.
Well, yeah, but so smaller than 49, 45.
Yeah, 45. So okay. So how
That's
far
5.
away? No, 49
Well,
minus, what's 49 minus 45?
4.
4. There you
oh my mic. I'm sorry, it's getting cold in here as this is going on, so I have to put on my blanket.
That arithmetic though. Okay.
Yo, I was thinking about what multiple of 9.
Oh, what the quotient was.
Yeah, so 4 or
Yeah,
9
that's the thing.
times
That's
5
the thing.
is 45.
We don't care about the quotient. We don't care about the quotient. Yeah. But it's easy to get confused. Which one do we care about and which one do we not care about, right? Because we're throwing away some information. So you just have to remember to throw away the correct information. Okay. So now let's do 4. So, okay, sorry, 7 cubed. So instead of doing 7 cubed, we can just multiply 7 into 4. Because remember, each like little line here is just multiplication by 7, right? So since we're reducing mod 9, we only have to multiply by 4. Sorry, by 7.
Okay.
So what's 7 times 4?
28.
28. And then what's 28 mod 9?
27. No,
1.
1.
The wrong one. 1. Oh.
I did it.
So look, we found our pattern, right?
Woo!
We're back to 1. So now we
It's
can
also
fill in.
4.
No, it's 3. 174,
Oh
174, and so
goodness.
on and so forth. So now our loop is length 4, right? So if we
Okay.
made a picture, it would look like this: 174, and then we would have.
You just said my loop is length 4.
No, our loop is length 3.
Yeah, okay. There you go.
So multiplication by 7, multiplication by 7, multiplication by 7, and then here in the middle, we're working modulo 9. So actually, like, we're guaranteed to have a loop that's shorter than 6 for the number 9 for reasons that have to do with Euler's generalization of Fermat theorem. It just turns out in this case, you get the length is 3. So that's cool. So that's a little bit easier. Okay, so now keeping that in mind that the length is 3, how are we going to approach this problem right here?
I don't know. You tell me, Michael.
So read this. So read to me this highlighted thing.
Oh, so we're gonna yeah. So we're gonna take the 7, whatever that big number was, the 3-digit number. You can
Yeah.
divide it
Well,
by
no,
3.
just read that. Yeah. Okay. Good. Yeah, you're going to divide that by 3.
Yeah,
So the
431 divided by 3.
yeah. So 431 divided by 3. Let's do that together. So 3
Thank you.
dividing into 431. Okay. So tell me what to do. Is it
I
over
thought
there?
somebody was
Someone doing
knocking
it over there for you?
Yeah, no. I thought somebody was knocking on my door. Okay. 3 goes into 4 once.
Boom.
4 minus 3 equals 1. Okay. Michael, I was gonna get to the bring down the 3 part, but you got it. 3 goes into 13 4 times. That's 12. So and then 1. And then you can bring down the 1. And
Okay.
then 3 goes into that twice. No.
Nope. Yep.
3
No, that's
times.
right. No,
It,
3 times is right.
3. I got it. 9. So 11 minus 9.
Try
2.
again. 2. So that means 431. 431 is congruent to 2 modulo 3. So that's pretty important for this problem. Also, like, a little bit unrelated, but how beautiful is this? You have 431 here, and here you have 143. Isn't that kind of cool? Same digits?
Well, it would be cool if it was 1 3 4, but
no, I think it's cool like this. It's like we did it's like we started reading right here instead of reading right here. So 431. 431.
yeah, I stand by what I
431.
said.
It's like been cycled. 431. 431. Hey, people, comment in the comments. Comment in the comments. Isn't that cool? Also, is something mathematically going on there? It might be. Okay.
Also,
so now
do you think it would be cooler if it was 1 3 4?
So this is going on my math channel, so a lot of people are going to watch it, just by the way. So there will actually be comments, unlike our unsuccessful podcast, which I urge all of you to subscribe to. If you like how bantery we are, we're more bantery on the podcast. I'm a little disappointed with Grace right now, actually.
Why? On this? To not be bantering on this?
Yeah.
I thought I was supposed to be professional.
Okay.
I'm already looking stupid, Michael.
No, you're looking great.
I can't be acting like a brat on here.
I think you're looking great. Comment. Is Grace looking great? Mathematically,
thank you.
Okay.
We don't need any hate comments today.
All right, let's finish this one off. Because our loop is length 4, the exponent can be reduced mod 4. So over here, that would read, because our loop is length 3, the exponent can be reduced mod 3. We did that. So that means that 7, 4, 3, 1 is congruent to what mod 9? So it's first congruent to 7 to what power?
2.
2. Because of this, right? Then what's 7 to the 2 mod 9 by our chart?
4.
We got yeah, 4. 4 mod 9 because of our chart. Yeah. So the chart serves two purposes, right? So it sets up the length of the loop, right? The length of the loop is given by the chart, and this like final calculating step is also set up by the chart, right?
Yeah, cool.
Yeah, you seem convinced of its coolness.
It's dope, dude. It's dope.
I'm sorry we're not discussing Sartre, or isn't that a philosopher?
I don't know.
Okay.
I don't know.
So let's
we're
gonna put it all together in an example, and then you're gonna work the final one out. Dum dum dum. Okay. So putting it all together, this is a warm up for the final goal, the big goal.
Jesus Christ.
So find the last digit of 1, 2, 3 to the 4, 5, 6. Okay. So step number 1 is, well, if we're trying to find the last digit, we reduce mod what?
10.
10. So 1, 2, 3 to the 4, 5, 6 is congruent to 3 to the 4, 5, 6 modulo 10. Right?
Yeah. Can you just give me a second? I'm going to write all this down so I can follow these steps after.
Great.
Yeah. Continue.
Okay. So that's our first step. So that's something you noticed that a while ago, right? So that was pretty sweet. And now what we're going to do is look for a pattern in powers of 3 mod 10. Right?
Yeah.
So that's the next thing we need to do. Look for a pattern in powers of 3 mod 10. So let's do that. We'll do.
Do we have to make a chart?
3 yeah, exactly. 3 to the k, and then 3 to the k modulo 10. And we're going to make our chart fairly long because we don't know like what the length of this loop will be. I mean, I know because there's Fermat theorem, or Euler's generalization of Fermat theorem tells me how long
You
it
can
should
just
be.
say you're smart, Michael.
But a priori, you don't know how long it will be. So let's go 5, 6, 7, 8, and then we'll add more if we have to, but we won't have to. Okay, so build this chart. So what's 3 to the 0?
Oh, I was finishing my chart.
Okay.
1.
3 to the 1.
3.
3 squared.
That's gonna be 9. 4.
No. Look, because we're working mod 10 now. So it's just 9.
Oh, so it's just 9.
Yeah.
So now we don't care about. Oh, it's because the mod is 10.
Yeah, because the mod is 10. This is situational. Yeah, the mod is 10. Okay. And now what's 3 cubed? So that's going to be 3 times 9.
27.
27?
Yeah.
So mod 10?
7.
7. Yahtzee. Now what's 3 to the 4th?
That's going to be 9 times 9.
Yeah, okay, that's a good way to think of it. So what's 9 times 9?
Right. 9 times 9, 81.
81. Mod 10?
1.
1. Hey, go. So we found our loop, right?
And our loop is 4.
It's 4. So now we can fill in the rest. 3, 9, 7, 1, and then that continues forever. If we wanted to put it up here as a picture, I'm psyched about putting it up here like a picture. 9, 7. What about you? What does the picture do for you?
The picture does nothing.
Really?
Well, I mean, especially when you get to this part where you're about to do times by 10 or 3, that poof.
Really?
Because I have to make a intellectual leap as to why 7 times 3 equals 1.
Because we're working mod 10, which is like in the middle.
Yeah, you see, it's just not instinctual for me. But that's just me.
I like the picture.
Anyway, it doesn't matter. I'm sure. Yeah, the picture's nice. It's pretty.
I think we could sell a shirt with that picture.
I think you can sell a shirt with that picture. I will be leaving after.
All funds go to the podcast,
which goes straight to Michael.
No, which goes to buying podcasting gear for you guys.
Oh, we just got a text from my dear brother.
Yeah, I know who bailed, but you know, whatever. Maybe I'll do
He
something
didn't
like this.
bail. He didn't bail.
No, he did bail.
He just accidentally didn't wake up.
Yeah, that's bailing.
Are we gonna record something after this?
Yeah, we could do that. Yeah, you could tell us how this was. This is gonna be great.
Yeah, I'm texting Alex.
Yeah, no, I recognize that. Just like give me more editing to do on this video. Don't worry about it. LOL bet. You're so Gen Z. Are you gonna say something like this? Man, this math trick that Michael taught me, it slaps.
Oh, buddy. That's a good one. Should you be ready by 1:45?
We're pretty close. Yeah. That gives us a chance to finish and then me get some water.
A little bit. Yeah, what's wrong with that? Okay. Yeah.
So let's look at this. You ready?
Yeah.
Okay. So now that means based off of this down here, because our loop is length 4, the exponent can be reduced mod 4. The loop is length 4 over here again. Right? So let's extend this down. So 1, 2, 3 to the 4, 5, 6 is congruent to 3 to the 4, 5, 6, which is congruent to, now let's reduce this 4, 5, 6 mod 4. Do you want to do that together? Yeah.
Wait, is this the third step?
Yeah.
Is step 3?
Maybe. I don't
write
know.
it. Well, you said first and then the
good
second.
Good point. I was not consistent.
No.
Second.
There you go. Clear steps. There we go. Okay. So
4 dividing into 4, 5, 6, right? That's what we need to do. So tell me what that is.
Wait, why are you doing 4 divided into 4, 5, 6?
Yeah, you tell me.
Because are you doing like the mod thing?
I'm reducing 4. I'm reducing 4, 5, 6 mod 4 because my loop is length 4.
Oh.
Yeah. Okay. So what do we get?
Oh, give me a second. I'm writing it out. Wait, 4, 5. Okay, so 4 goes into 4 once. 4 to 0. Bring down the 5. 4 goes into 5 once. You got 11, then you got 16. 4 goes into 16. 4 times? 4 times. 4 times?
4 times.
4 times. We have no remainder.
Yeah. Remainder 0. So this is the same thing as 3 to the 0.
So.
Which is what?
1.
1.
Wait, so 3, 4, 5, 6 is equal or is congruent to
1 mod 10.
Oh, okay. So that means given this congruency thing you got going on, 1, 2, 3 to the 4, 5, 6 is congruent to 1 mod 10.
Yeah.
Dope.
Now, before we do the final one, let's do this. There we got it. 1, 2, 3 to the 4, 5, 6. We're going to actually calculate it and make sure it's 1. Okay. So let's make this a little bit bigger. No, let's make this a little bit bigger. Look at the last digit there.
What?
It worked.
What?
So now we're to this last thing.
Why isn't it? Oh, hold on. I'm sorry. My laptop's going to die.
Yeah, you got to fix that.
Okay, so yeah, it's plugged now. Yeah, it's plugged in. Okay, continue.
Okay, so now we're to our big goal. Big goal. So 4723 to the 8675. Okay. So what do I do?
Well, we're going to do mod 10.
Okay, so tell me what that means.
So we're going to take 8 675 and divide it by 4.
Wait, you got a step before that.
Oh, okay. Well, I was just kind of, yeah. Okay, so that's going to be 3 to the 8, 675 because it's
Yep.
mod 10.
Yep. And then luckily, so this is
You
lucky.
have to write mod 10. Write mod 10.
All right. Okay, so now luckily we have the same base down here. We still have the number 3, right? So that means our loop is the same. If we had another number there, perhaps our loop would be different, okay? So, but since we have 3 there, the loop is the same. Okay, so now what are you going to do?
Now you're going to take the 8675
8675
and divide it by 4 because that's
okay.
the loop. And so you got 4 goes into 8 2 times, bring down the 6, 4 goes into 6 once, then you get the 2, bring down the 7, 4 goes into 27. 4, 8, 12, 16, 20, 24. I don't know why I had to do that. 1, 2, 6. So it goes in 6 times. That's 24. And that's 3. Bring down the 5. Oh boy. 4 goes into 35. How many times? Not like 7.
8.
8. 4 times 8 is 32.
Call back to earlier in this video.
Hey, okay. Then we have a remainder 3.
Remainder 3. So tell me what's your next line. You're going to say that this is congruent to.
Well, you got 2165 in the thingamabobber.
Yeah, that doesn't matter so much. All that matters is the remainder. Oh, you want me to do this?
Yeah. 6, 8. There you go. Now, so hold on. Let me make sense of this. The remainder is 3. So that means it's 3 to the 7 or 3 to the 3rd. Mod 10.
Which is, don't get flustered. What's 3 times 3?
9.
9 times 3?
327.
The answer is
27 mod 10.
Reduce that last digit. What's 27 mod 10?
Oh, I was like, I can't reduce the mod 10. 27.
So that tells us the last digit
is 7.
Of 4723 to the 8675 is 7. Not 7 factorial 7. Okay. So just to finish this whole thing off, let's check it. Should we check it? Mathematica. Okay, so there we've got it. 4723 to the 8675. So let's push go on this. Boom. So look, the number's big. Like, that's big, right? Would you agree to that that's a big number?
I already saw the last number.
Yeah. So let's make it bigger so that everyone can see. Now it's even bigger because I made the type big.
What a big number.
We did it.
What?
Goal.
Yes.
Okay. So good. Thanks for playing along, Grace. So I had a really good time doing this. Let's do this from time to time. I think it's fun. Like maybe once every other month or something sounds like a good thing. Post in the comments if you like this video. Actually, it's sort of my dream to do a series where I teach huge YouTubers math. So if anyone out there has connections with enormous YouTubers, I think that we could really make math popular, which is going to make the world a better place. I might seem like I'm being sarcastic, but I'm not being sarcastic. I think
Yeah, I
that
really
is
don't
one of the
think you're being
keys
sarcastic.
to making the world a better place. So if you enjoyed this, if you enjoyed the banter with Grace and stuff, make sure to subscribe. Yeah, subscribe is the word. Subscribe to our podcast. It's quite fun. We get into a lot of hijinks. Um, and anyway, now I'm signing off. I guess I usually say this is a good place to stop.